Here's a classic that some of you may not remember. What's the difference between an egg and an elephant? If you don't know, I am not going to ask you to go to the store to buy a dozen eggs, because you never know what you're going to come back with. So, enough of my bad jokes. So, in parallel with that, what's the difference between a cooling tower and a geothermal loop field? If you don't know, do I dare ask you to design a geothermal system? So it's sort of a corollary to the egg and elephant joke. And I'm going to preface a little bit just looking at a fundamental energy quiz. And I see Winter's on the call, and I know you're the energy analyst. Since you're the energy person, which one of these uses more energy?
And how long they're on?
Perfect answer. So, would you believe 4 times more energy? Take a hairdryer that might be used 5 minutes a day. Every day of the year, it's 56 kilowatt hours a year. And that 60-watt light bulb, if on 10 hours a day, it might be some security light or something, or all the phantom loads in your house. I monitor my house, and when I think everything is off, I'm still using 300 watts. So it's to keep your TV warm enough to turn on quickly and so forth. So you can't judge energy with demand or power. Watts or kilowatts are a unit of demand. And loop field sizing is a function of energy, not demand. And the unique aspect, energy flows in both directions. You've got heat of extraction, heat of rejection. So it's different approach than a cooling tower, which 99% of cooling towers probably just reject heat one way. And the last characteristic of a loop field is the thermal capacitance. If you take a 20-foot diameter circle, 500 feet deep, you're dealing with 25,000 tons of material. So as we extract heat or put heat into the ground, there's an enormous amount of thermal capacitance. You got to think of it more like a battery that also leaks energy to the ground. So you ultimately can lose heat into the ground, but there's an enormous amount that stays within close proximity of our loop in the ground. Does a 200-ton data center have the same energy profile as a 200-ton office building? I would say a 200-ton cooling tower could be applied on each of these jobs. However, the same loop field could not be applied on these two different jobs. The foundation of any geothermal loop design is a realistic, full year, 87, 60-hour energy model. And I underline realistic. I've had engineering firms give me their energy model for me to model a geothermal loop field. And one example was a modest-sized school. They had an enrollment of 600 people. And as I dug into their energy model, they had nearly 2,000 people in this building all the time that the school was open. So you've got to be realistic. Most energy modeling is done to compare system A to system B. And the absolute are not necessarily as important as the relative number. So A 4-pipe VAV system might be 10% better than some other system. And that kind of relative comparison is a great use for an energy model, unless it's realistic with schedules and lighting and demand controlled ventilation that you are trying to capture as realistic as possible. That model is not good enough for geothermal. So I encourage energy modeling, but also try to be realistic. Yes, we always tend to put safety factors and make sure we don't get in trouble. But if you do it too much, the size of your loop field gets much bigger, and we're not really serving our client as well as we should be. Because the number one problem with geothermal that everybody cites is they cost too much. So the challenge is to be realistic, to be cost effective. Yes, we don't want to get in trouble, but that's where experience over time will really help make decisions. There's lots of design tools out there for doing energy modeling. I'm sure you've got one of these that you're comfortable with. We use the Carrier Half program when we do modeling, but there's a lot of them out there that can do a very good job as long as you're putting the proper inputs into the software. Loop field sizing, very dependent on local geologic characteristics and formation temperature. And it can vary widely all over the country, and certainly even in New York State, which I'm very familiar with. Up in the North Country, ground temperatures could be 46 degrees on average. You get down to Long Island, which is only a few hundred miles away, it's probably closer to 55 or 56 degrees. I've done work in Florida where the ground temperature may be 75 degrees, so you got to be aware of that. The thermal conductivity, the ability of the soil to conduct heat. The other characteristic, which is very important, is thermal diffusivity, really reflecting the capacitance of the ground. Moisture content, that includes hydrogeologic formations that may be fairly active. I did a project 10 miles from here, and at 286 feet down, we hit a 6-foot void, which was actually an underground river. That could have a tremendous impact on how well that loop field actually works. The loop configuration, there's so many varieties of people trying to come up with different piping geometries, bisect tubing, spider loops, 4 loops down a single borehole like the twister. So those all have a bearing, but not as much as some of the other parameters. Grout thermal characteristics is very important. We tend to want to make it almost equal to the ground conductivity. So if you've got a formation that has a conductivity of 1.4, well, I would suggest the grout should be at least 1.2 and up to 1.4 conductivity as well. Otherwise, it tends to act like an insulator. Our good friends at Aztec Geothermal, an upstate New York company, does thermal conductivity testing. It's pumping heated water into the ground. You measure the amount of energy because you're heating that water with an electric resistance heater. You've got a flow meter. You're circulating that heat so you know exactly how much heat you're putting into the ground. And then you monitor how the temperature changes, typically over a 48-hour period. So if it's a very good formation from a heat transfer standpoint, those temperatures won't get as high. If it's not so good, you'll notice the temperatures getting higher. And from that data, we can back out those parameters, the conductivity, and to some degree, the diffusivity values. My own company has conducted about 200 thermal conductivity tests over the last 25 years or so. So we populate a Google map with our data. We also open this data up to anybody who wants to contribute conductivity tests they may have in their library. So Galen, I'll invite you to send us your conductivity test reports. We'll put it on the map, and then we'll send you the link so you have access to this whole map.
Yeah, I
It's
think we have
proven.
a few probably that we can give you.
Yep. So we're more than glad to share it, but we want it to be a partnership and get access to some of the data you may have. We also have a Google Sheet that goes along with this that has direct links to the actual report. So you get a little more detail of geology, the drill log, and so forth. So that's available. We have design tools that can take those thermal properties of the earth and then predict how much feet of pipe you need in the ground based on all those parameters, configuration, and so forth. Now, we happen to use LoopLink Pro, which has quite a history to it, developed by Ryan Sarda and Doug Carruthers at GeoConnections. They were ultimately bought out by Dandelion. Dandelion still has the software in their bailiwick, but I find it very cost effective and it seems to work pretty well. But obviously, there's other softwares out there that have their pros and cons. So what I want to talk about for a minute is this thing I call the delusion of precision. We calculate loads to the nearest BTU per hour. I've seen loads expressed with 5 or 6 significant digits. And we believe that it's that accurate. But if I gave the same set of drawings and thermal characteristics of a building to 10 different engineers, I'm sure I'd get about 11 different answers. So it's nice that we calculate it, but let's not fool ourselves into thinking it's as precise as the number of significant digits would indicate. We also calculate loop lengths to the nearest foot. I get a kick out of designs where I see the engineer calls out something like 383 feet. And I scratch my head. I say, most distributors of pipe might carry it in 50-foot loop length increments. So it might be good just to round it up to the nearest 50 foot because it's not that precise. Our tools are good, but they're no way that precise. We express both of these as being extremely accurate. But when we calculate pressure drop and select pumps, it's not far off from wetting our finger and sticking it up in the air. I'll illustrate that by using this example of when does 1 1/4 not equal 1 1/4. And what I've got plotted here is all the different pipe materials I've seen used in a geothermal system. The two on the left, PVC and steel, I'm not a big fan of, but they are used. And then I've got a whole bunch of high-density polyethylene with different DRs. We have polypropylene in here with a DR9. We've got copper, type L copper. We've got hose kits. We've got PEX tubing. They're all available in nominal 1 1/4 size. If we look at the inside diameter of each of these, you start to see a disparity. So 1 1/4 is not actually 1 1/4, but it's not diameter we're interested in, it's area. So once we square that radius and calculate area, the disparity grows. And then it's not area that's important, it's actually velocity. At 12 gallons a minute, here's the different velocities going through these different pipe sizes and materials. Now, pressure drop is a square of velocity. So this is what you end up with across 1.25-inch pipes or tubing. And there's tremendous difference. And I don't believe many people really calculate pressure drops looking closely at these numbers. So that is what drove us to try to develop a piece of software that can help tackle these calculations as accurately as we're tackling loads and loop length. So that gave rise to our software, GeoDesignPro. But I want to spend a little time talking about it. Our mission was threefold. We wanted it to be accurate. We also wanted it to be comprehensive, to serve a variety of functions that engineers have to wrestle with and try to put it all under one tool or one umbrella. And last, it's got to be fast. If I don't save you time, as well as improve your accuracy, I'm sure you're not going to be interested in. So we tried to create the user interface that made things happen real time and quickly. As far as accuracy, here's a formula that tries to calculate pressure drop in a pipe. And you can see it's a function of velocity squared, density, length, diameter, and a friction factor that has embedded in it not only the piping material itself, but the Reynolds number influences friction factor. And you may recognize this as the Darcy-Weisbach equation. It's considered the gold standard in the industry as far as calculating pressure drop. But all too often, we fall victim to tables and charts that are great for one particular set of circumstances. Like I was taught by IGSFA that to account for propylene glycol, you calculate with water and then multiply by 1.34. I don't think that's accurate enough. So that's what drove us to incorporate this kind of logic into our software. Also, we've got an extensive library of pipe materials and sizes from 3/4-inch to 24-inch, each having its own unique diameter and roughness factor. These are essential for pressure drop and internal volume. Fittings are incorporated with equivalent length, thanks to Galen's feedback, but those equivalent lengths are ignored when it comes to calculating volume. Also, antifreeze impact. You specify what freeze point you want, and the program will calculate the exact volume of antifreeze required based on its own density at the lowest water temperature you specify as part of your design. So as you stipulate minimum entering water temperature as well as desired freeze point, you're getting accurate properties of the fluid, which could be propylene glycol, methanol, or ethanol. Pipe size selection. The program uses simple logic to recommend pipe sizes, trying to keep the velocity above 1.5 feet per second. So it finds the largest size pipe that has that velocity of 1.5 feet per second or higher. So those calculations are done in the background, and the program populates the diameter with a recommended size, which override. We've incorporated the pressure drop. You can put in a diversity factor, internal volume, antifreeze amount expressed in gallons, diameter size of reverse return manifold. Every segment is pre-calculated with the ability to override it. Fittings, export CAD drawings. It'll tell you how to balance a loop field without using balance valves. It gives you flush and purge flow and head requirements. Optimizes valve manifold design. It'll allow you to fully configure a heat pump to identify every digit in the model number so it doesn't leave certain aspects of the heat pump up to chance or the contractor deciding those things for you. It'll create a schedule of heat pumps. You can export that schedule to a spreadsheet. There's more Easter eggs. If any of you drive a Tesla, you know Elon Musk enjoys putting Easter eggs into their software. So hopefully you can find some of those in our software. So this is the sign-up page. There is no charge for this software. I won't promise that'll last forever, but that's our goal, is to get widespread usage so we get the collective feedback from all the users. You sign in or create a new account, and we'll start on the project tab. Most of it's self-explanatory. You can specify min-max water temperatures, your flow rate per ton, a diversity factor, which I think is often overlooked when designing proper pumping systems. Antifreeze freeze point. What I'll talk about, these icons down here. Phoenix Energy Supply can provide these heat pumps, but more importantly, each of these icons is linked directly to the manufacturer's website. So if you need a piece of information like the physical size or some other attribute of one of these heat pumps, you can get it quickly. We're not solely going to represent the heat pumps we can sell, but we put water furnace in here. One of our users wanted water furnace, and I'm glad to put other heat pumps into the software as well. And those icons will also be linked to the manufacturer's websites. One part I want to point out, we've incorporated what we call book tech support. Click that button. You can request 30 minutes of one-on-one discussion with myself or maybe Brandon, depending on what you want to review with us. And it's not necessarily limited to the software issues. If you've got other questions regarding geothermal, this is a vehicle you can use to set up a Zoom call and do a one-on-one meeting. Zones. This is where you can identify all the zones being heated or cooled. And the user interface is fairly easy to use. You can add a zone. You can build up the number of heat pumps. You can override the default tag values. You can name each zone. You put your heating and cooling loads in kilobTUs per hour. We don't need to put all 5 digits or more in there. Specify the manufacturer, the series. The software will pick a tonnage for you, but I caution you, this is based on the AHRI closed loop rating. So if your application is significantly different, then you can override the choice the software made and pick any size you'd like. You got flow rates, pipe material, diameters, length, number of elbows, and a CV value for typically a two-way valve. You may have strainers. If both a two-way valve and a strainer, you put the CVs of both separated by a comma, and it will calculate an equivalent CV. Now I'm going to blow up that little color chart, and this illustrates where the pressure drop is occurring in that circuit. The first part is the heat pump. And you'll notice it's red, but the ones down below are green. And it's just a tickler. It's telling you that maybe the pressure drop of your devices, the piping, the valve you chose, is too big. Those are items you have control of. The color will change when you get the pressure drop of the heat pump to be at least 70% of that circuit. You're not going to be able to change the pressure drop of the heat pump, but you can change the piping diameter, perhaps, the CV of a two-way valve. In this case, we look at the CV of the two-way valve. This particular heat pump operates at 12 GPM. We got a CV of 10. My rule of thumb is I'd like to get close to twice the flow rate. Now, there's a particular valve I like, a Belimo 1-inch valve that has a CV of 19. And as soon as I change that CV value from 10 to 19, the heat pump becomes over 70% of the total pressure drop. So it's a guide to give you feedback in selecting parts that you do have control of. Let's say you don't want to spend the time to build out all your heat pumps, and you want to look at just analyzing the loop field. So as soon as you check that box, you get a pop-up window where all you have to do is specify a flow rate. Maybe you know the nominal tonnage of the building. Throw in a flow rate that corresponds to that tonnage, somewhere between 2.25 and 3 GPM per ton. The internal pressure drop, you're just putting it in there as a guess of what you hope to have the pressure drop of the internal piping to be. There's also an input for internal volume. And one thing you'll notice with our software, we have tool tips. And here's one that pops up on the internal volume. It's a percent of loop field volume. Anywhere from 5 to 20% is pretty typical. So you put a percentage in there that's reasonable. So once you do this and move on to the loop field tab, you can define your loop field. And here's an example of, we've got 5 bores of 1.5-inch pipe, DR11, going 500 feet deep with a reverse return manifold. We've got 20 feet of tapped spacing between the loops, a total length of run-out pipe going out to the middle of the reverse return manifold. We always ask, go to the middle of the manifold, because the supply pipe is probably going to be shorter, but the return pipe is going to be longer. That's a length from the interior valve manifold, whether it's in a vault or in a mechanical room. So you specify that length, specify the diameter. Similar to our heat pump circuit, we have a similar color-coded feedback of where is that pressure drop occurring. Is it in the run-out pipe? Is it in the vertical loop? Or is it in the reverse return manifold? And if it's green, that tells us our loop is at least 70% of the total pressure drop. Go down to the bottom of the screen, you'll see our next group, labeled Group 2. The red indicates that particular loop is at 69%. It's feedback to open your eyes to options you may have to improve pressure drop and avoid excessive pressure drop with run-out pipe and manifolds. One of the things I really was challenged to figure out how to do this was actually generate the CAD drawing. Down on the lower right, you generate that, and it'll make a drawing. This has actually been improved just in the last few days because we were missing part numbers over here on the elbow. I wanted a little more padding on the left, so it's doing a little better job. But it basically tells you the diameter of each segment of that reverse return manifold. It also gives you the exact fittings required to make these in the field, and these will all roll forward into the bill of materials. This is a simple manifold. You can download this as a DXF and paste it into your own CAD drawings. But then you can have much bigger manifolds, hard to see. And we've got tools at the top, the magnifying glass. You can blow it up and see the details. In this particular junction, we're going from a 4-inch down to a 3-inch with 3/4-inch loops. So it's automatically calling out a 4x4 butt fusion T with a branch that is a 1-inch socket fusion. They don't make a 4x4 by 3/4. They also don't make a 4x3 reducing T. So it calls out the other parts you need. Butt fusion reducer from 4 to 3-inch. It also calls out a socket fusion coupling from 1-inch to 3/4 so you can reduce down and connect to the loop. The next piece of information, you get this summary of loop data. It tells you what's the total flow rate, how many feet of bore in total, the GPM per 100 feet of bore. And this is a parameter I've gotten used to looking at. And I would say if that's between 1.5 and 2.5 GPM per ton, your loop field is properly sized. If it gets too low, if you're down to 1 GPM per 100 feet, chances are the loop field is oversized. If you get up to 3 or 4 GPM per 100 feet, chances are the loop field is undersized. So it's sort of a sanity check. It gives you that loop pressure drop and the internal volume of the loop field. And over on the right, we try to keep a running tab of some of these key parameters. The next item, we've moved this table up into the individual groups recently, but I want to use this table, and I'll blow that up, to illustrate a way to balance loop fields. And I get a kick out of the number of interior valve manifolds that are calling out balance valves. To me, I'll be candid, it's a waste of money. We can design loop fields without putting permanent pressure drops in a system. And the irony is nobody uses them to balance a loop field. Every job I've ever been on that has balance valves, they're all wide open. Nobody tweaked it. Nobody put a manometer on it to dial it in so they were perfectly balanced. So I encourage you, stay away from balance valves. So this illustrates we've got 3 groups. The first one's got 8 bores, second one 9 bores, the third one 10 bores. Significantly different as far as distance away from the building. Very unusual. Typically, groups might only be 20 feet apart. But here, the site dictated we spread them way apart. Our design flow rate is basically we want the same GPM per foot of pipe on all our vertical bores. And that's how we calculate the design GPM. But the program will calculate what the actual pressure drop is based on how the flow will naturally balance. In this extreme case, the closest loop is going to be 18% over design, and the furthest group is going to be 15% under design. Now, you can debate whether or not that is a problem. Personally, I don't think it is. Keeping in mind you're sending the same temperature water out to all these groups. So the one that's got 18% more flow will simply have an 18% lower temperature change. And when we're dealing with temperature changes in loop fields, ideally it's about 6 degrees in heating, 12 degrees in cooling. In reality, the jobs I see are more like 4 or 5 degrees because we're over pumping the loop field. Let's say it is 12 degrees in cooling. We're going out at 95 and coming back at 83. if we've got the balance across those three loops, the temperature change is going to be roughly 10 degrees on group one and maybe 14 degrees on the third group. But when they all come back together again and mix within that return manifold, it's going to be that 12 degrees. So I challenge the need to have perfect balance, but to satisfy those engineers who want perfect balance, I would suggest mixing and matching different diameters in the runout pipe. You end up putting smaller pipe in the closest group. You're building an extra 9.8 feet of pressure drop in that runout pipe, or 5.6 feet of head in that middle group. Instead of reducing pipe sizes on those closer groups, I'm going to increase the pipe size going out to the third group. So when I bump that up to 3-inch from 2-inch and make minor tweaks on the other groups, I can achieve a plus or minus 3% balance. I've reduced the pressure drop by roughly 20%, as opposed to a balance valve that even in a wide open position will have a pressure drop of at least 5 feet of head and maybe more, depending on the particular valve. Balance valves that I see are typically only accurate to plus or minus 5% anyway. I would encourage you to look at other ways to achieve balance if you feel that balance is that important. Going on to the distribution tab, this one was a bit challenging to develop, and we've evolved it some maybe from those early days. Basically, all the heat pumps show up in the unassigned zones, their tag, which if you changed it, I had somebody who wanted it to match tags on a drawing that they didn't make the drawing, so the engineer made up his own tags. I said, absolutely. Put the tags that are on the drawing on your zone tab. That way you can know where they are a little easier. With a simple drag and drop, you can drop all 5 of those heat pumps into one distribution circuit. You can specify room numbers where that heat pump might be located, pipe material, number of elbows. It'll tell you the flow rate. And what you're really modeling is the piping upstream of that junction or node. The first node is going to feed HP1. With good eyes, you can see that it puts the name of the zone and the heat pump size in the description on the left. You're modeling what's upstream of that T that's feeding the heat pump. The program will automatically pick a diameter based on keeping the velocity above 1.5 feet per second. It'll tell you the pressure drop in that upstream pipe. If for any reason they aren't fed in this order, you can simply drag and drop them in a different order and it will recalculate everything. We also have a section to handle the mechanical room. And I'll blow that up so it's easier to see. Let's say you've got 20 feet of DR11 4-inch pipe in the mechanical room connecting everything together. You may have 6 elbows. We built in a bypass function so that some guys like to have a continuous side stream filter coming off the discharge of the pump going back into the return. If you want to incorporate that in your design, you put a flow rate here that corresponds to that filter. It goes into the total flow that the pump has to produce, but doesn't change the pressure drop of the system. You can incorporate CVs of the various hardware. It might be an air separator, it might be a triple duty valve, any number of things. You just put them all in a sequence separated by commas. It calculates the equivalent CV. It'll also tell you the velocity With this low of velocity in the mechanical room, I might be tempted to drop it down to 3-inch. It'll give you the pressure drop. So just another facet of our tool. Moving on to the Flow Center tab. And this is a recent addition based on expansion tank sizing. All too often, I've seen jobs with enormous expansion tanks. And the program will look at the modulus of elasticity of polyethylene pipe. More importantly, it looks at it over long term. Polyethylene pipe has the ability to creep, and if subjected to higher pressures or different temperatures over time, that pipe will respond. And that's the time frame our system behaves in months. There's the modulus of elasticity for polyethylene. If you were to suddenly shock it, has a strength of like 150,000 psi. But over time, that drops to 50,000. And as a result, the volume of your system will change over time. It also looks at the properties of the fluid and how that expands and contracts from one season to another. Here's a reasonable project where the minimum pressure you want to see might be 15 psi, the maximum of 27, and that's dictated by this expected winter pressure. The unique thing about geothermal, the pressure change in the system is counterintuitive. The pressure actually goes up as the loop gets colder. So we display that up here, that if you set your minimum at 15, we're assuming that's going to be in the summertime. And then it calculates the expected pressure in the wintertime. And that results in roughly a 12 psi swing from winter to summer. But if you wanted to tighten that up, say you wanted it only 1 psi, it'll tell you you need an expansion tank capable of handling 24.6 gallons of fluid. Look at the tank characteristics and make sure it can accommodate that much volume. The tank may be bigger than that. But this was a handy tool that one of our users wanted us to look into. So we did make a video about the whole expansion tank calculation methodology. Dropping down to flow centers, I appreciate your support here, Galen, as far as our GX Flow Center. It has become a fairly successful product for us. We started working on it about 15 years ago, and it has evolved. We have a variety of GX Flow Centers available. The industry has other flow centers in the top row for typically smaller systems. Our GX, the biggest one, is a dual primary secondary. So we've got essentially 4 pumps that can handle up to about 300 gallons a minute, give or take. But let's say our client wanted 2 pumps for redundancy. The program will identify those dual pump flow centers that meet your need. It'll tell you whether it's partially redundant, which means under peak load, you have to run both pumps, or full redundancy so that one pump could handle the whole system. And the pumps will automatically do lead lag on their own. It will illustrate the head capability at the flow rate. The system needs 51.5 GPM. It'll indicate the head available from these pumps at that flow rate. It'll list these flow centers in order of lowest to highest cost. But let's say you're not interested in any of our GX flow centers. Well, that's fine with us. We'd like to sell GX flow centers. But we understand that this is not going to be the perfect fit for every job. So we give you the option to custom select your own. You click that. You can enter any description you want as far as a pumping station, And for the sake of job cost estimating, you could put in a budget cost for that. So that would be selected and show up in your bill of materials. Moving on to the schedule tab, and the magic button, I think, is what we call configure. You click on configure, you'll get a pop-up window with the model number of that particular heat pump with the underscores representing where you have options. A cabinet configuration, vertical or horizontal. Do you want a de-superheater or not? Do you want copper or Cooper nickel heat exchangers? We identify all those. It completes the full model number, adjusts the list price. So now you've got a completely identified heat pump. But the job's not over. You may want accessories. Go into the accessory tab, specify thermostats that are available from the manufacturer. The one we're going to illustrate today is an IntelliZone, a zoning package that GeoStar offers. We can configure the zoning package. So we click on that. You tell it how many extra zone thermostats do you want? Well, I want 3 more. So that's a total of 4 zones. You get 1 zone with the basic package. You got 3 extra zone stats. You can specify zone dampers. You can add dampers, both rectangular or round. You can put the dimensions in. You can specify 3-wire or 2-wire. It'll give you the part number of the damper, a list price. It'll give you a CFM that damper is nominally good for. And it's based on 500 feet a minute of airflow. You can drop that down or increase it at the risk of potentially adding noise if you go too high. Configure the full system, get the list price of this package. Once you get done configuring your heat pumps, you not only get the model number, but it'll look up, populate your schedule with all the appropriate electrical data. From there, export it to an Excel spreadsheet, do any customization, and drop it into your drawings. The bill of materials. Everything you've loaded up to this point gets rolled forward. The costs aren't all that accurate. We're going to refine that as we go forward. Certainly the heat pumps are all accurate. We feel some of our users want to keep track of coming up with a cost estimate for a project. Moving on to the report tab, it essentially is going to put in tables throughout this report that reflect all your inputs and outputs. This little magic button will generate an AR narrative and put it in text, a description. Click that, it'll generate an executive summary, as well as the various sections of the report will also have their own narrative. You can export it as a PDF or export Excel, which exports all the tables in an Excel format. So you can easily edit them as you see fit. The last is the feedback tab or contact tab. We want to hear from you, whether it's issues or refinements to the software that you'd like to see. Please use this. I'm also going to remind you of the book tech support function. I encourage you, if you want to have a one-on-one quick discussion, I encourage you to do that. And then last, questions. If you're sitting there scratching your head, I encourage you to reach out to us. I'd love to hear if you've got any questions.